Hello everyone, welcome to my first class at Vedantu JEE English. I believe I'm finally live in front of you guys. If I am audible and visible, please write you in the chat box, you know the drill, yes. What's going on, people? It's been a long time that I've taken an entire class in English. I hope I still have the knack for it. But yeah, today we are going to do one of my favorite topics of the entire syllabus of JEE, and that is general organic chemistry, including some bits of isomerism as well. Now, since this is a previous year question solving class, we would go question by question, and behind those questions, whatever theory there is, we would try to discuss it there and then, right? Now, in case you wish to learn organic chemistry from me throughout, then I would tell you where to go in some time, all right? People, are we ready for this? Very nice. Chalo. So the first question that we have is a question from the stability of carbocations, right? The decreasing order of hydride affinity for the following carbocations is. What does it mean, hydride affinity? What is a hydride? What do we mean by a hydride? Hydride is essentially an H negative ion. Yes. So what this question asks you is that out of these four carbocations, which one wants to capture a negative charge badly? Which one just wants to capture a negative charge, and which one is happy with the situation it is in? Okay. So it's talking about the stability of the carbocations. If your carbocation is unstable, it would want to capture a negative charge very quickly. But if the carbocation itself is relatively stable, then you can take your time. You don't need to capture a negative charge in a hurry. Yes? So, the decreasing order of hydride affinity, what does that mean? It means you have to give me the increasing order of stability. Yes? So, my dear friends, let's just talk about the stability over here. Which one of these carbocations is the most stable? Can you tell me that? Which one of these carbocations is the most stable according to you? And for those of you who are worrying about the theory behind all of this, don't worry. I will discuss the theory related to the questions while solving questions itself. But if you want to go deep into theory, I will tell you where to go in some time. Okay? Cool. So people, look at this one. This carbocation is a special case for us. Alright. What's so special about this carbocation? Does anyone know? It's known as a cyclopropyl type carbocation. See, what happens over here is something really interesting, and you need to pay attention to this. Questions from this will directly be asked in your examinations. There's a high probability that this year as well, you will get an application of this somewhere or the other, right? So people, what happens in this cyclopropyl system is something really peculiar. What we expect over here are these straight bonds, right? What do we have over here? We have 3 carbon to carbon sigma bonds, right? Now, when we visualize sigma bonds, what do we imagine? We imagine something like this. There's, let's say, a p orbital overlapping with another p orbital in a head-on fashion, right? That is how we imagine a sigma orbital. But the thing over here is that if these 3 bonds between the carbons are pure sigma bonds, then there is a catch. Then the problem is that these bond angles would all be 60 degrees. Yes. These are sp3 carbons. sp3 carbons want to have a relatively chilled out bond angle, 109.5 degrees, yes. But over here, if you're forcing them to form a 60-degree bond angle, do you realize there's going to be a lot of strain over there? There's going to be a lot of angular strain if the bond angle over here is actually a 60-degree bond angle. So when scientists did a little more research behind the structure of this particular species, they realized that the orbital overlap is not as simple as just a simple sigma bond. Okay, the orbital overlap over here is very peculiar. Let me try to show you how it works. So you have these three carbons. This is what we had imagined. Let me put that in dotted lines. Now, this is the overlapping p orbital of this carbon. This is the overlapping p orbital of this carbon. This is another overlapping orbital of this carbon. The overlap between these p orbitals is neither properly sigma nor entirely pi. This is a sigma overlap, this is a pi overlap, right? But over here in this cyclopropane system, the carbon-carbon bonding is very peculiar. It's neither a proper sigma bond nor an entire pi bond. It's somewhere in the middle. Yes? Can you see that? What this does is this allows the cyclopropane to exist without having so much angular strain over here. Yes, now that you can see the overlap is different, there's not a lot of angular strain over here. Yes. Now what happens is when we have another carbon over here, which is technically a carbocation. What's a carbocation? Carbocation is essentially a vacant p orbital. Carbocation is when you have no electrons in a p orbital, vacant p orbital. So make that vacant p orbital over here. Now, my dear friends, I would love for you to think about the basic criteria for resonance. What was the first criteria for resonance? The first criteria for resonance was that you need to have parallel orbitals. If orbitals are parallel to each other, then electrons can access all those orbitals, yes? For instance, if we draw the structure of benzene, do you realize all the orbitals over here are parallel to each other? Yes or no, people? And that is why the 6 electrons that are there in this resonating system are delocalized throughout. Parallel orbitals basically have wave functions that can overlap with each other. Think about the orbitals like waves. Yeah, these waves are close to each other, they are parallel to each other, so their wave functions can constructively interfere with each other. Constructive interference. Remember? So, for constructive interference of orbitals, the first criteria is that the orbitals need to be parallel to each other. Now notice, given the kind of system that this cyclopropane has formed, if you have a vacant p orbital over here, I'll write a small positive over here to signify that it's a carbocation. Do you see that the electrons that are occupying this orbital can also delocalize over here? This and this orbital will also form a very good constructive interference between them, and therefore the electrons that lie in this orbital can find themselves some more space in the vacant p orbital over here. Alright, so this is the special case of a cyclopropyl carbocation. Cyclopropyl carbocations are exceptionally stable. And the fun fact is that since these carbocations were found to be stable in nature, since when scientists were doing reactions, they found out that okay, this type of a carbocation is exceptionally stable. That's how they came up with this structure. So these carbocations being stable are a testament to the fact that yes, this structure exists in this manner, right? So my dear friends, always remember that a cyclopropyl carbocation is exceptionally stable. Now, if you search for this online, you know what you will find. I'm trying to look for that in the chat box. Yeah. People who want me to speed up, don't worry. As we keep going through questions, we'll speed up as well. Also, if you want to watch my classes at a higher speed, then you can watch them later after the live stream is done. You can watch them at 2x speed as well. Yeah. Very nice. Mr. Gamers has said dancing resonance. Yeah. So if you search online for dancing resonance, then something like this will turn up for you. Let me tell you a very nice story. Dancing resonance is not really a scientifically published concept. What's published is something like this, where the orbitals are overlapping with each other. Now, how some Indian teachers have explained it is that they've said that there is special resonance over here, in the sense that this bond breaks apart and forms a double bond over here. So they make a resonating structure like this, okay? This is what they'll do. So they'll keep breaking these sigma bonds to do resonance with the carbocation. This is not published in any scientific journal. This is only something that was devised by our famous old teachers of Kota. You know Kota, right, in Rajasthan, where JEE classes were so popular. So this is a derivation of Kota teachers, dancing resonance. They've given this name only so that the students could remember it. So this picture, take it with a pinch of salt. This perhaps is not the best way to explain it. This surely is. So anyway, coming back to the question, the most stable carbocation over here is D. So it does not want to capture any hydride ion. Yeah. So this D does not want to capture any hydride ion. Yeah. Least tendency to capture a hydride ion. Then the next one would be this one. Benzene rings associated with a C positive. So benzene will give its mesomeric effect. Everyone knows benzene is a very good, system for resonance. So cool. B is also pretty stable. Now the comparison comes between C and A. It's very simple to do this comparison because this carbocation is also in resonance with this double bond. Yes, there's a p orbital over here, there's a p orbital over here, and there's a vacant p orbital over here, 3 orbitals in conjugation with each other, right? So there's a resonance over here, but in this carbocation there is no resonance, there is only hyperconjugation. Yes, there is only and only hyperconjugation because of these protons. Over here as well there is some hyperconjugation, but resonance is always given more priority over hyperconjugation, so keep that in your mind. So out of these two, which one will be more stable? A. So that does not want to capture the hydride as much. And then the most amount of desire for a hydride ion lies with C. So if this is the order you gave for this question, you are absolutely correct. Now, in the process of me explaining this question, if you have any doubts, you can ask me right now in the chat box. All right. From the sections of general organic chemistry and isomerism, in your examination, you can expect anywhere from 1 to 2 questions. Okay, so 4 to 8 marks is something that you can expect out of this particular segment. Tarun, just refresh the page. I am actually streaming at 1080p 60 FPS. Okay, so refresh and see whether the video quality in your thing is fine. Naveen, thank you so much. Luxury Hitler remembers my dialogues as well. Very nice. Zizi is asking, does benzene show plus M or minus M effect? See, since, do you remember this idea? Electronegativity versus S character. Let's say there is a singly bonded carbon versus a doubly bonded carbon versus a triply bonded carbon. So this guy, the electronegativity of the sp carbon will be higher. Higher is the S character, higher is the electronegativity. Keep that in your mind. So this one is sp, this is sp2, and this is an sp3 carbon, yes. So electronegativity will be higher for this, then this one, then this one. So the highest electronegativity lies with C triple bond, then double bond. Since in benzene you have C double bonds, yes, the electronegativity is generally higher than any other carbon, which is sp3 in nature. So benzene tends to have a very slight minus M effect. Very slight. Okay, fine. Great for JEE 2024 is saying, but the thumbnail shows 20 marks. Because clickbait, my dear friend. And the other thing is that from general organic chemistry, all the concepts that you learn will be useful in other chapters as well. So perhaps you will have questions of, syn addition onto a trans structure. Then you would have to judge the stereochemistry of the final product. So for that you need to understand optical isomerism. So therefore the applications of this chapter are vast. That's why it's an important chapter, right? So my dear friends, before I explain to you this question, alright, this question is of nomenclature, by the way. Give me the IUPAC name, as simple as that. Let's see how many of you can do that correctly in the chat box. And by the time you figure out the name for this particular lengthy molecule, let me tell you, if you want to study organic chemistry properly, there are no shortcuts. Organic chemistry cannot be rushed through. You have to sit down, take your time and study organic chemistry. Now, out of the ones who are watching this class live or recorded, if you are someone who does not really enjoy chemistry right now, if you are weak at organic chemistry, if you want to make organic chemistry your strong point, then you need to spend time on it. So if your organic chemistry is very weak right now, you have to think about the longer game. You have to think about making it perfect by the time you have your second attempt of JEE. By the first attempt, do as best as you can, but organic chemistry cannot be rushed ever. So you have to spend time learning it step by step, because organic chemistry is like one big TV series. If you directly start from the aldehydes ketones chapter and study nothing before that, you won't understand that chapter at all, right? So if you want to study GOC from me, which is the starting point of organic chemistry, which is very important, you can go to YouTube and search for this very nice series of mine called Epic GOC. There are 10 lectures in Epic GOC. Every lecture is just 1 hour. And in these 10 lectures, you will become an expert at GOC. So 10 days and I'm sure you'll be better than anyone else around you in GOC in case you want to do that. Cool? Chalo badhiya. Now let's do this question. So if you look at this question without any options, this might look like a difficult question, right? Interesting. Epic GOC is in English, Nadia. Epic GOC is in English. See, I've always been teaching in English. It's just the last 6-7 months that I've been teaching in Hindi on Vedantu JEE. Otherwise, I've always been a teacher who teaches in English. So all of my past videos that are there on YouTube on Vedantu JEE or Catalysis by Vedantu, all of them are in English. They're really popular as well and they're really helpful. So you can check those out. So if you look at this question just like this without any options, it looks very difficult. Yeah. So let me tell you, in nomenclature, what you have to remember is just some simple ideas. First simple idea that you have to remember is that carboxylic acids always take high priority. Okay. So if you ever see a carboxylic acid anywhere in the entire structure, you just give it number 1. Carboxylic acids will always get the higher priority. You will always name this as something oic acid. It's a carboxylic acid. Now let's figure out the longest chain. 1, 2, 3, 4, 5 and 6. So you understand that whatever your answer is, it is some hexanoic acid. Yeah, it is some hexanoic acid. Now in this hexanoic acid on the position 2, you have a methyl. And on position 5, you have this group called oxo. If you didn't remember this, I'm telling you now, C double bond O group, when it's considered as a different group, yeah, when it is considered as a prefix in the nomenclature, it is called oxo. If this was the main functional group, this would be a ketone, right? But it's not the main functional group over here because we have an acid. So this becomes an oxo group. So there's an oxo on the 5 position, there's a methyl on the 2 position. Now, I'm going to ask you a very difficult question. M versus O. Which one appears first in the alphabet? A, B, C, D, E, F, G, H, I, J, K, L, M comes first, and then you have O, right? So alphabetically, M comes first, therefore you will start the name with 2-methyl, and then 5-oxo, then hexanoic acid. Alright, fine. We figured out the name, but do you realize that if you had the options for this, which you will have in your examination, the question becomes way easier. Have a look. This is how the question will come in your examination. Now look at the options. Now look at the options. Doesn't this become extremely simple now? You know that there's a methyl on the 2 position. You know there's an oxo on the 5 position. 2-formyl rejected, 5-methyl rejected, 5-formyl rejected. The only option that you're remaining with is this one. You didn't even have to figure out the entire name. Just looking at the options, it's so easy to reject the statements. The point being that a lot of students spend unnecessary time brooding over nomenclature. That's not necessary. Okay? You don't need to sit in one place for 10 hours learning about nomenclature. That's not necessary at all. Just brush through nomenclature from the NCERT for 1 hour and that's enough, because you will have options in your examination. And these options will easily help you navigate through all questions of nomenclature. They are very easy. Alright? So, I can see Totapalli Yashwant has a doubt. Please ask me, alright? Great, Fajay, thank you so much. LL Kumaran is asking, what is formyl? Can anyone tell what is formyl? What is formyl then? What is formyl? Achha, I'll give you a hint, okay? I'll give you a hint, you figure it out on your own. What is formyl? This is formic acid. That's the hint I'll give you. Okay? Fine. So everyone who is new to my classes, welcome. My name is Pahul. I'm an alumnus of IIT Bombay. I've been teaching in English for a really long time now. So all of the knowledge that I have of chemistry is on YouTube in English for all of you. In case you want to watch my classes, just search for it on YouTube, you'll get it. You can write hydrocarbons Pahul Sir English, you can write GOC Pahul Sir English, or you can write epic GOC, whatever chapter, electrochemistry, chemical kinetics, atomic structure. I've done all the classes in English, so you can search for them easily on YouTube and get it. Cool. Most of the videos will be on Vedantu's channels, Vedantu JEE and Catalysis by Vedantu. Cool. Very nice. Now let's do this one. This is a very simple question, by the way. I would love for you guys to do this as quickly as you can. The descending order of acidity for the following carboxylic acids is. So you've been given acetic acid derivatives. Yeah? Acetic acid derivatives. This is your acetic acid. Yes. CH3COH is known as acetic acid. Now you have trifluoroacetic acid, monochloroacetic acid, etc., etc. So all of these are acetic acid derivatives, right? Now, my dear friends, you have to remember this idea that when you have electron withdrawing groups, okay, listen to this carefully, and I'll give you a very nice trick to remember this in case you are a new student of mine. Electron withdrawing groups, all right, always tend to increase the acidic character. Alright, whenever you have electron withdrawing groups present in an acid, they would tend to increase the acidic strength of your system. An easier way to remember this is, I'll tell you, this is just a, you have to remember this, release, decrease, alright, release, decrease, withdraw, Badhao. Badhao means increase in Hindi. So it's a very nice rhyme. Release, decrease, withdraw, badhao. Yeah. So this is something that you can remember, and instead of thinking about this entire statement every time you watch a question, every time you look at a question, you don't need to. You just need to think release, decrease, withdraw, badhao. So just remember this for acidity. Cool. क्या लिख दिया मैंने यहाँ पे? Acidity. Yep. So for acidity, release, decrease, withdraw, badhao. The more withdrawing effect there is, the more is your acidic strength. As simple as that. For basicity, this will be entirely opposite. So all you need to remember is this statement: acidity, release, decrease. Everything follows obviously. So over here, what will be the strongest acid? The one with the highest withdrawing character. This one, trifluoroacetic acid. 3 fluorines. Fluorine is the highest electronegativity system. I mean, fluorine is the most electronegative atom in the entire periodic table. Yes. So 3 fluorines, they'll withdraw a lot of electrons with inductive effect, and therefore B has the highest acidic strength. Then you have between these 3, fluorine, chlorine, bromine. Again, fluorine wins. Then you have chlorine. Then you have bromine. And then finally, am I doing it correctly? Yeah. And then finally you have the normal acetic acid. So if this is the order that you've written, good job. Cool. As simple as that. Now, what we've considered over here is their minus I effect. Minus I effect comes from electronegativity. More electronegativity means more minus I effect. Can anyone tell me why we did not consider resonance over here? Why did we only consider inductive effect? Why didn't we consider resonance? What's the reason? Tarun, yes. For all of you who have seen my GOC classes from the Epic GOC series, these questions are going to be extremely simple for you. Yeah, but since this is a JEE Main previous year question, I have to do this. So why did we not consider resonance? We didn't consider resonance because, my dear friends, this carbon over here in all of these cases is an sp3 carbon. sp3 carbons don't show conjugation. Yeah, you need to have an sp2 carbon. You need to have p orbitals that are, either in pi bonds or non-bonded, or you need a lone pair, etc., etc. So simple sp3 carbons don't participate in resonance. That's why. Cool. So let's go to the next question now. Standard question from the very basics. And even though it is from the very basics, a lot of people will do it incorrectly in the examination because basics is one thing which no one really knows well. So let's revise our basics. Resonance in the carbonate ion, CO3 to negative. So there's a carbonate ion that's given. You've been given 3 resonating structures for it, right? First you have oxygens over here with the negative charges, then the negative charges go around, double bond moves, so on and so forth. So 3 resonating structures are given. Now you have to pick the true statement out of the following. Let's read these one by one, okay? The first statement says it is possible to identify each structure individually by some physical or chemical method. Can you isolate one of these structures separately? The second question says all these structures are in dynamic equilibrium with each other. Now this structure exists, but then it converts into this one, then it converts into this one, and these exist in dynamic equilibrium with each other. Each structure exists for an equal amount of time. And then finally you have. So my dear friends, let me remind you that resonance is an imaginary idea. What we draw as resonating structures are all imaginary structures. What exists in reality is a very beautiful structure that's been decided by nature. In that beautiful structure, what's happening is that this carbon, this oxygen, and this oxygen, their wave functions, their orbitals are in constructive interference with each other. What's bonding? Bonding is essentially just constructive interference between two electronic wave functions. So this particular molecule exists in a manner that the wave functions of all of these are in a very beautiful constructive interference with each other, and they have formed a very beautiful structure, and all the electrons are existing throughout. It's just our inability to comprehend nature directly that we have to imagine these petty little resonance structures. Resonating structures are imaginary. We draw them on paper and we imagine them. Why do we imagine them? Because when we are writing reaction mechanisms in organic chemistry, it becomes easier for us to figure out where the attack is going to happen. Electrophile will attack in this position, nucleophile will attack in that position, etc. So just for the ease of understanding, we define these imaginary resonating structures. What exists in reality is a very beautiful structure which is called the resonance hybrid or the resonating hybrid. Fine. So CO3 negative has a single structure that is called the resonating hybrid, and that is technically speaking a hybrid of all of these three structures. So if you have to draw the resonating hybrid, what you will do is you will form a single bond between these three, and then you will form a partial double bond at all 3 points, and then you will distribute the negative charges equally. That's what your resonating hybrid looks like. The energy of the resonating hybrid is lower than all of these resonating structures. That's why this exists, right? What exists in nature is stable, it has low energy. So these resonating hybrids are all imaginary. Sorry, these resonating structures are all imaginary. This hybrid is the reality. So first three statements are incorrect. Option D is the only correct statement. Chalo, basics are also revised with this one. Let's move on to the next question. So there are 4 conformers given to you. Can you tell me which one is the most stable conformer? Can anyone tell me which one out of these is the most stable conformer? What compound is this, people? Tarun, yes, you can watch my class even if you haven't seen Epic GOC. That's not a problem. And whoever has a doubt, you can simply ask your doubt in the chat box. Whenever I get to see the chat box, I'll answer that doubt as well. Alright. This is butane, right? There are 4 conformations of butane that are given. So in butane, what happens is there's a methyl at the front, there's a methyl at the back. Yeah. This is what your butane looks like. So when you look at it from the side view, it looks like this. These are known as Newman projections. Cool. So when this methyl and this methyl are right in front of each other, they will have a lot of steric hindrance. Yeah. This methyl, they are in a straight line right now. So there's a carbon, there are 3 hydrogens on it. There's a carbon, there are 3 hydrogens on it. So these will repel each other. So this system will be unstable. So you want to keep them as far as possible. Which one of these has methyls as far as possible? The first one. Can you believe it? This is a JEE question. This came this year in JEE. JEE main chemistry is extremely easy. All you need to do is just have faith in yourself. Alright. So my dear friends, the angle that you see from this perspective, yeah, right now the angle is 0 degrees, right now the angle is some acute angle, now the angle is 90 degrees, Now the angle is 180 degrees. So this angle between these two methyl groups is known as the dihedral angle. This angle between these two methyl groups is known as the dihedral angle. Fine. Just keep that in your mind. So this conformation is the most stable conformation. It is also known as the anti-conformation. Yeah. This conformation is called the anti-conformation. Yes. This one is known as what? What's this conformation known as? This is known as a gauche conformation. Don't call it gotcha, please. Okay. What is this one known as? This is known as a partly or partially eclipsed conformation. What do you mean by eclipse? When something hides something at the back. Yeah. When do you have a solar eclipse? When the moon hides the sun. That's what it is, right? So, eclipsed means that there's a hydrogen right behind methyl. There's an atom right behind the front one. So this is an eclipse conformation. But since methyl is not right behind methyl, we call it partially eclipsed or partly eclipsed. This one is fully eclipsed. Methyl right in front of methyl. So this one is known as the fully eclipsed conformation. Now someone was asking, sir, why is there a ring over here? That's just so that the structure looks good. Instead of drawing the structure like this, that will look very shabby, right? So what we do is we denote the front carbon with this. I mean, this is the front carbon and the back carbon is denoted with the ring. That's what it means. Alright? Cool. Ashik is saying, isn't gauche supposed to be the most stable? No. The anti-form is supposed to be the most stable one. The gauche is relatively stabler compared to the eclipse forms. Alright, coolio. Let's move on to the next question. So as you can see, people, the JEE main questions from general organic chemistry are extremely simple. JEE main questions throughout chemistry are extremely simple. So if you continue your journey of JEE with me till JEE Advanced, then when we come closer to JEE Advanced, then I will do high level questions with you as well. Alright, cool. Someone is asking, can we call those interactions flagpole interactions instead of dihedral interactions? See, the term flagpole is used in the case of cyclohexane. So it's just a name given to those interactions. You don't need to worry too much about the names. Cool. The black caps is saying JAB taking over though, sir. I know, but I'm actually hopeful that JAB will bring forth more logical questions in JEE Main. Yeah. Deepak is asking, sir, what is a staggered conformation? So, see, staggered is a general idea. Okay. This is a staggered conformation. This is a staggered conformation. The specific name for this staggered configuration is anti. The specific name for this staggered configuration is gauche. Staggered is where eclipse is not happening. Eclipsed is where you have atoms right behind each other. Staggered is something like this. This could be a staggered form. This could be a staggered form. This specific staggered form where methyls are absolutely 180 degrees apart from each other, this one is known as the anti-form. Okay, this is a special case of the staggered form wherein methyls are at 60 degrees from each other, so it's called a gauche form. Alright, Akhila, it will be a total of an hour and a half, maybe 2 hours. Let's see. So let's do this question now. So there are two statements over here. Okay. There's this very interesting compound that they've given and they've asked you whether it's optically active or not. Then the second statement says whether this is the mirror image of this one. And then you had some statements to follow. You've been given 4 statements. You had to choose which one is the right option. So let's just look at these structures and spend some time on it because this is actually a good question. Yeah, let's look at it. So what's been asked in the first question is this structure, is it optically active? Can you see? Can you check? What do you think? Is the first one optically active? I am looking at the chat box. Okay, let me do one thing. I'll draw that structure for you properly over here so that you can see it, because in phone screens this might not be that visible. So this is what the structure looks like, okay? There is a geometrical isomerism type thing happening over here. There is an NO2 towards the front. Yeah, this wedge means that there is an NO2 that's coming towards you, and there is a dashed hydrogen, means the hydrogen is going away from you. Then this thing continues and there is another, there is a structure like this. Cool, this is what's going on. So the question asks whether this is optically active or not. Now a lot of people are saying, no, this is not optically active. Are you ready for a nice ride in this question with me? This question will take us for a ride. Take a deep breath. Let's think about it. Is this optically active? Yes or no? Think. Optical activity comes out of orientation of certain things in space. Yes or no? Orientation of certain things in space, that is what decides optical activity. Now we have simplified that idea to asymmetry and chiral carbons and groups not being the same on carbons, and we've simplified it. But what's the ultimate idea of optical activity? That if you have something that's asymmetric from its mirror image, yeah? If I have a structure, if I make its mirror image and those two are not superimposable onto each other, then that will give you optical activity, chirality, yes? Now over here what we can see is that this is potentially a chiral carbon. This can be a chiral carbon because there are 4 groups on it. One is a nitro group, one is a hydrogen group, but then the other 2 groups that you see look very similar, don't they? Carbon, carbon double bond CH3, carbon, carbon double bond CH3. Seemingly they are very similar to each other. This is also carbon, carbon, 3 carbons with 1 double bond, 3 carbons with 1 double bond. They look very similar, but do you realize that both of their orientations in space are different from each other? This will always have such a shape because this is a cis isomer, yes? And this one has a different shape. Stop thinking about the molecules over there. Stop thinking about the carbons, bonds, etc. Think about the shape. Do you realize that the shape of this particular branch will always be different from the shape of this particular branch? Yes. Optical activity talks about the asymmetry in terms of the shape of the molecule. And we realize that on this carbon, the 4 things that are associated have different shapes. NO2 will have its own shape, hydrogen has its own shape, this guy has its own shape, this guy has its own shape. 4 things with different shapes on one carbon, that is how we decide chirality, right? Yes. So my dear friends, since cis is fixed in this kind of a shape and trans is fixed in this kind of a shape, their shapes make 4 of these groups have different symmetries in space. Getting the idea? So this carbon has 4 different groups around it. And that's why this is an optically active, this is a chiral carbon. So even though on paper they look same, but in reality this has a different shape, this has a different shape. And shape is what decides the symmetry and therefore the chirality. This is chiral, this is optically active. This is actually a very good question. Surprisingly, it came in JEE Main, but this is as good as a JEE Advanced question. Now Gaurav is asking, what if the double bonds were not there? If the double bonds were not there, then it would be optically inactive. Because if the double bonds are not there, then your shape is not fixed. Single bonds have conformation isomerism in them. Single bonds can easily move around. Yeah. So if this was just a single bonded system, this was just a single bonded system, then they could easily have the same shape. So only because of the double bond that we have over here, their shapes become fixed. Yeah. The cis shape is a cis shape, the trans shape is a trans shape, and therefore this is an optically active structure. Very nice. Now the next thing that I want you to do, now the next thing that I want all of you to figure out is the RS configuration of this carbon. Yeah, that's another trick that you need to figure out now. Just a second, let me draw that again. Dun, dun, dun. There you go. So now you have to tell me what's the configuration of this carbon, whether it is R or S configuration. CIP rules. First priority goes to nitrogen because higher atomic number, higher priority. Second priority will go to, now it's confusing, right? Because in CIP rules, we've never dealt with cis versus trans. This is a carbon, this is a carbon, then you have double bond carbon, then a single carbon, then a single carbon. How do we decide which one of these has a higher priority than the other? Tricky, right? So my dear friends, in such cases, these are very borderline cases, right? In such cases, if you have to decide the priority between this and this group, you give cis the higher priority, okay? In these specific cases, you give cis the higher priority. Why is this a specific case? Because the arrangement over here and the arrangement over here in terms of the molecules is the same. It's just that the shape is different. Yeah. So in such cases, you give cis the higher priority. It's just a convention, Kishore. There's nothing specific about it. Okay, RS configuration is only for writing on paper. It has nothing to do with the abilities of the compound as such. So you can decide whatever to call higher priority. And according to CIP rules, a very specific case, cis is getting higher priority, just for the sake of it. Alright. So you give higher priority this one, then the last one is hydrogen. And since hydrogen is already at the back, it's already going away from you, it's very easy. It becomes an S configuration. Yeah. Hydrogen is already going away from you, so this becomes an S configuration. Now all you need to do is check this structure. If this has S configuration, this is not a mirror image. If this has R configuration, this is a mirror image. Just check it out over here. First priority goes to the nitro, second priority goes to the cis, third priority goes to the trans structure. This is again S configuration. So the first compound is optically active, but the second compound that's given over here is not a mirror image. It's the same compound, just rotated and shown it to you. Okay, now Kishore is saying, what if we give trans more priority? Then in both cases you'll give trans more priority, then both of these structures will be R. Your question will be solved correctly. Yeah, that's the thing. They've not asked you for RS configuration, it's just an exercise I gave you. Even if in the examination you thought, okay, let me give R the higher, let me give trans the higher priority, that's also fine. You'll get both these structures as R, you'll get the correct answer, right? Nice question, right? So my dear friends, over here the first statement is correct, the second statement is incorrect, right? Mazedar question, I like it. So use this cis versus trans priority only when you have this borderline case. Very low probability of this turning up in your examination, but in case it does, now you know what to do, right? By the way, if let's say there is an OH group over here, then obviously this will get higher priority. Then don't do cis is higher priority than trans. No. Now there is OH group over here, there is no OH group over here, so definitely this gets a higher priority. So only when these two things are molecularly the same, then you give cis the higher priority. Just don't do that silly mistake. Anyway, nice question. So statement 1 is correct and 2 is incorrect. Option C was the correct answer over here. Chalo, let's do the next question. Batao, this is a very simple one. Which of these will undergo deprotonation the easiest? And don't worry, I will explain the logic behind this question as well. Kya baat hai? Haritanam is asking what is cross conjugation, and right then I have a question of cross conjugation for you. Elang is asking what's meant by RNS. So my dear friend, you should revise the classes of optical isomerism. You can search for them online, just write optical isomerism Pahul Sir, you'll get classes in English as well. So in optical isomerism, to judge configurations between two different enantiomers, we have R configuration and S configuration. So it's a long theory that you should study. It'll take some time, but just a suggestion from my side that you should study it. Okay. Otherwise, NCERT is not enough for general organic chemistry, honestly, because it's very sporadic, spread out in different chapters. So better you watch my classes. Okay. So let's do this question. Which one is easily deprotonated? Yeah, people. Let me do one thing. I'll take off the jacket. It's not that cold in here. Yes, I know. I had paused the audio so that you could look at the question and answer it. The jacket keeps rubbing with my beard and now the beard is nice and messy. Anyway, it is whatever it is. Chalo, let's do this now. So what you have to figure out is, this is the proton that you need to remove. Okay. And again the same concept will come over here, release, decrease, withdraw, badhao. That idea will come over here once again. This is the proton that we are looking at. Okay. This is the proton that we are looking at. So in order to abstract this proton, if say you abstract this proton, what will you form as the conjugate base? If you remove the acidic proton, then you will get a negative charge over here, a negative charge over here, a negative charge over here, and these are the three conjugate bases. Now, more stable is the conjugate base, better will be the acidic strength of the original compound. Yes, because if I'm forming a better compound at the end of the reaction, I'll do that reaction very quickly. So you need to figure out which of these conjugate bases is the most stable, and that one will undergo deprotonation easily. Cool. So now, over here comes the idea of cross conjugation. Let me try to explain to you what cross conjugation is. A lot of students get confused with this idea, but it's a very simple concept. Let's discuss it right now. Let's just look at this particular segment. Let me draw this segment once again over here for you guys. Yeah, Me means methyl group, CH3, okay? So don't get worried about it. Now, my dear friends, you have this double bond over here. What's the special thing about double bond O? Double bond O is highly electronegative, and whenever it can do resonance, it will always do a -M effect. Negative mesomeric effect. It would want to pull electrons toward itself via resonance. Yeah. Now the thing is, imagine you are this double bond O. Okay. This is you. You have to pull electrons. Now you have opportunities at both sides. You can either pull electrons from this side or you can pull electrons from this side. But the limitation is you can't do this. Okay, the limitation is you can pull electrons only from one side at a time. This is something that's not possible. Only one side. Okay, why only one side? Because out of these two bonds, only one is a pi bond. Resonance happens in pi bonding systems, yes. Resonance does not happen in sigma bonds. So over here, out of these two bonds, only one of them is a pi bond. So only one of them can help in pulling the electrons from either this side or this side. Now since you have two options, you have two options. So for some time you will try to pull electrons from here, then you will see, okay, I have a chance over there as well. Then you will pull electrons from here, then you will say, okay, I have a chance here. You will never be fully dedicated to one side. You are always sort of confused between these two options that you have. Double timing, always unstable. So my dear friends, this kind of a case where there is an opportunity to pull electrons from either side, this is something that is conflicting. You understand the meaning of conflicting? It's unstable. It creates a bad situation, sort of a personal argument. Yeah. So this is what we call cross conjugation. Cross conjugation is bad because neither are you focusing on one side nor are you focusing on the other. It's like those students who have to give NEET and JEE both. Those who have taken physics, chemistry, math and biology. So now neither can you give all your attention towards mathematics nor can you give all your attention towards biology. All the best. So cross conjugation is not good. Yeah. So this double bond O has capability to stabilize this because it can pull away its negative charge, but it can't utilize all of its capability over here. It is giving some of its capability towards this side as well. Cool. Over here in this system, there is no cross conjugation as such. Think about just the negative charge. This guy can also stabilize it. This guy can also stabilize it. You are getting stabilizing forces from two sides. A very good job. Stabilizing forces from two sides. You can also call this a cross conjugation, by the way. This is also a case of cross conjugation. But in this case, the cross conjugation is working in the favor of this. Because on both sides you have stability. Wherever this negative charge decides to go, it will get stability. Very nice. But this cross conjugation is not favorable for the negative charge over here. Because sometimes it stabilizes the negative charge, sometimes it does not. Over here also, on one side there is no problem. Yeah, this double bond O is fully dedicated towards this negative charge, fully stabilizing it with its own, all of its potential. The other one, it sometimes tries to stabilize the negative charge, sometimes it tries to resonate with the OCH3. No cross conjugation problems for the negative charge. This is the most stable conjugate base. Therefore, this will get protonated the easiest. Alright. Okay. So right now there are two students over here. Right now there are two students over here who are asking a very interesting question. I'll answer that question and then I'll move on to the next question. I'll just show the next question to you. So those of you who are not interested in that question can focus over here. Alright. So they're saying how to solve conversion questions. Do we need to remember all the reagents and what do they do in the reaction? And Dushyant is also asking, sir, how do we solve conversion questions? Do we need to remember all reagents? What do they do in the reaction? Perhaps the same student from two accounts. And do we need to solve conversion questions, remember all reagents, etc.? Okay. See, the thing is, the more you apply a concept while practicing, the better your mind will retain it. Alright. So all you need to do is keep solving questions. You will get acquainted with a lot of reagents while solving questions. The same reagent will come in different questions again and again. So if the same reagent, if the same pattern turns up in multiple questions that you practice throughout your preparation time, your brain will automatically remember what the reagent does. You won't have to specifically go and cram up reactions. Alright. So it will happen with practice, and we will continue our organic chemistry practice with these sessions, and the closer we get to the examination, the intensity of these sessions will increase. Okay? So this is a standard question, by the way. It's given in the NCERT as Tamil IITian has mentioned. Yeah, this is a very standard case of basic strength of amines. Now tell me, people, should I just do this question in short, or do you want me to explain the funda behind this? If you want to do this question in short, just write short. If you want me to explain the funda behind this, it will take like 10 minutes. Write funda in the chat box, I'll tell it to you. And now that I've been speaking for over 2 hours straight, my throat is starting to give up. Hot water. Cool. So since people are asking about funda, I'll try to explain it to you as briefly but as succinctly as I can. Okay, let's see. My dear friends, when we talk about basic character of amines, amines have this lone pair on them. Yeah? Nitrogenous compounds are amines, nitrogenous organic compounds are amines. Now, over here, if I have to use this as a base, what will happen? If I have an H positive, the lone pair will go and capture the proton. This is what basic character is. Yeah. Now, how will I increase the basic character? If I increase the intensity of negative character on the lone pair, the basic character will increase. I told you acidity release decrease. The opposite will be true for basicity. Basicity release increase. The more electrons you give towards the lone pair becomes stronger and goes and captures a proton very easily. Yeah, fine. So over here, if I have these 4 amines for you, let's say I have ammonia, then I have NH2 with a CH3 on it. Yeah. Then I have, let's say, an NH with 2 CH3s on it. And then I have a nitrogen with 3 CH3s on it. Which one will have the higher basic character? Just looking at this idea, just thinking about this funda that I've shown you. Over here, there is more inductive effect from the CH3s. More CH3s, more plus I effect. CH3s have a plus I effect, I'm sure you remember. So there is a lot of plus I over here. There is lesser plus I over here. There is very less plus I over here. There is no plus I over here. So just because of the inductive effect, this lone pair is very basic in nature. Only because of the inductive effect. This is funda number 1. That because of inductive effect, more inductive effect implies more basic strength. Okay. But now, in reality, we do acid-base reactions inside water. Yes. 99% of the times, whatever acid-base reactions we do, we'll do them in water. So in water, let's try to understand what will happen to their conjugate acids. Inductive effect, okay, fine. But now let's think about their conjugate acids inside water. Yeah, these are the conjugate acids. Conjugate acid means they have already captured an extra proton. The lone pair has been utilized and now there is this positive charge on top of it. Now, my dear friends, when you throw these in water, when they are formed inside water, water will try to solvate these ions. Do you understand solvation? What is solvation? Water has a dipole moment on it, yes? Hydrogen has a partial positive character, oxygen has a partial negative character. So this water molecule's negative character will get attracted to this positive character. Yes. So what will happen is I will denote the water molecule like this. Okay. This is the bent water molecule. This is how I will write it for the ease of drawing it. So this pointy end is the oxygen and these exits are your hydrogens. Okay, this vertex is your oxygen. So my dear friend, look at this. This is a very small ion, right? There are only hydrogens across the nitrogen. So what will happen is lots of water molecules will come and surround it. Lots of water molecules. Lots of solvation, which means this is very stable. Lots of solvation is happening. Lots of water molecules are coming closer to this positive charge. Positive charge comes close to the negative charge of water. Stabilization. Energy is released. This becomes very happy. This will be happy but not as much because there is a CH3 stopping water from coming from this side. Steric hindrance. So water molecules will only be able to come from these sides. From here no water molecule can come. So this will also be happy but not as happy as this guy. 2 degree case, solvation can happen only from here. Yeah, lots of steric hindrance from this side. So this will also be occasionally happy. This is very happy, this is happy, this is like okay fine, I'm not too sad with my life. This guy, there is hardly any solvation available. Water molecules will not be able to come close to the center because there are so many methyl groups present stopping the water molecules from coming because of steric hindrance. So the only position where it can get some solvation from is this. So this is sort of sad. Now do you understand that to judge the basic character, there are 2 factors, not just one. The first factor was the inductive effect. More inductive effect gives more basic strength. The second effect is now that you have formed the conjugate base, what about the hydration effect? What about the solvation effect? So according to solvation effect, do you see the opposite is true? According to solvation, this is good. According to solvation, this should quickly make this ion and become happy with water. So there is one effect going in this direction, the other effect is going in this direction. 2 effects opposite to each other are affecting your basic strength. So how do we decide? How do we decide what's the final order? We do an experiment. When there are 2 ideas going opposite to each other and these 2 ideas are necessary for you to decide the final outcome, you can't predict. You don't know whether inductive effect is more important here or whether hydration is more important. Which case, what's the balance of those 2 ideas? So all you do is take these structures to the laboratory, throw them in water and do an experiment. And when you do an experiment, you find out that after the balance of that inductive effect concept and this solvation concept, finally the order that comes out is, where's the question? Here you go. Finally, the order that you get for methyl amines is this one. Inductive effect and your solvation effect both balanced out finally give you this order of basic strength inside water in an aqueous solution. 2 degree methylamine is the most basic. It has a good balance of inductive effect as well as solvation. Methylamine, trimethylamine and just ammonia. So this is the order that you have to remember for methyl amines. Now that I have explained the idea to you, I have a little homework for you for this particular question. What you have to do is you have to try and figure out the order for ethylamines. Okay. Find out basicity order for ethylamines. Okay. So just keep it in your mind that this exceptional order, you can call it an exception if you want, This order where inductive effect and solvation are going opposite to each other, this happens only in the case of aqueous medium. Polar protic solvents can do solvation, and that is when you get this idea. If you've been asked a question, what's the correct order of basic strength in gaseous state? What's the correct order of basic strength in a non-polar medium? Then in a non-polar medium or in a gaseous state, you will not have the considerations of solvation at all. You will simply give the basic strength according to inductive effect if the medium is not aqueous. Keep that in your mind. Alright. Haritanam is saying rules in physics everyone in the universe obeys. Rules in chemistry, I don't give a about your rules. Haritanam, do you realize how wrong your statement is? It might create a good meme, but chemistry is fact. Chemistry is what we directly observe from the nature. Physics, on the other hand, the physics that you study is very far from nature. The first chapter that you study in physics, what do you assume? Frictionless surfaces, massless pulleys, coefficient of friction is static throughout, plane surfaces, static coefficient of friction is fixed, dynamic coefficient of friction is also fixed. Very nice, wow. I know, Aritaram, I am not taking it seriously, but I am clarifying the fact that the entirety of physics that you study is exceptional because, I shouldn't call it exceptional, but you are working on assumptions that do not exist in the real world. Anyway. So, let's do the next question. The number of stereoisomers possible for 1,2-dimethyl cyclopropane. Batao. One 2-dimethyl cyclopropane, the number of stereoisomers possible. What is 1,2-dimethyl cyclopropane? There you go. Very beautiful question. Try to figure out the answer, people. This is a good question. I can already see people stumbling all over the place. By the way, if you haven't hit the like button, please do so. Alright. Tanisha, so the thing is that I was called on this channel sort of late in the journey of the preparation. So my sessions will be question solving sessions mostly, but then there are some sessions where I will focus a little more on theory. So I'll try to strike a balance between both. Neither session will be totally theory or totally questions. It will always be a balance of both things. That's because we are so close to the examinations. Now, once the first attempt of JEE Main is done, then I might take some theory-centric one-shots as well. Arey yaar, why have I drawn pentane? Very sorry. Thank you so much for correcting me, Omar. 1,2-dimethyl cyclopropane. Arey yaar. I'm sorry. Look. Thank you so much. Although the answer will be the same, but thank you for correcting me in the structure. So my dear friends, over here, if you notice, if I draw a Haworth projection, the first stereoisomer. See, stereoisomer means you have to consider both geometrical isomers and optical isomers. So the first thing that I can see over here is this particular structure. This is what cis 1,2-dimethyl cyclopropane. Yeah. Do you realize that this structure has a very nice plane of symmetry running through the middle? Yeah. Plane of symmetry, I can cut this structure into two equal halves. Since there is a plane of symmetry, this is an optically inactive compound. Okay? So this is one of the stereoisomers. But now things get interesting when we make the transform. Check this out. Is there a plane of symmetry over here? No. Try to make its mirror image, please. This is the mirror image. Now do whatever you have, use whatever energy you have, try to superimpose. Try to superimpose these two structures. I guarantee you they will not be superimposable. It's not possible to superimpose these two structures on each other. Yeah, just look at this. Can you see my hands? These are mirror images right now. Can I superimpose this part on this? I can't. The thumbs will always be pointing in different directions. Thumbs are pointing in different directions. Thumbs are not even close to each other. No matter what I do. These two mirror images can't be superimposed onto each other. The same thing happens over here. Yeah. So the trans case has two optical isomers. So overall, what's the number of stereoisomers that you got? 1, 2, and 3. 3 stereoisomers. Are you able to imagine this in 3D, by the way? This is not a flat structure. Okay, this is not a flat structure, this is a 3-dimensional structure. I'll try to draw that for you over here in a different way. So this is the central bond, this one, okay, and the carbon over here, this is, you can imagine it something like this, going away from you behind the plane of the board. Okay, so this is kept flat on the screen. It's not like this, it's like this. Cool. And then one carbon is somewhere over here and the other one is somewhere over here. Easier to imagine? Yeah. That triangle is lying flat on your table, let's say. One CH3 is going here, the other CH3 is going here. Got it? Do I have a piece of paper that I can use to explain this to you? Let me see if I can fold it into a triangle. Yeah, Haritanam, I know, man. I know that feeling. I remember in my JEE 2011, I still remember that question because I have been teaching that question since a lot of years. There was a question from ortho effect. I knew that ortho effect question is gonna come in the examination. I still did it incorrectly. I lost 4 random marks in the examination because of that one question. I still remember that. This is what's going on, people. So this is the triangle. It's lying on the desk. This is a CH3, this is the other CH3. Cool. So this is one isomer and this is the other isomer. So both of these are not superimposable on each other. Cool. Chalo. Very nice. How difficult is this? Not at all. Batao ye. You have to tell me the answer. I am not going to do this question for you. As I said, looking at the options, it's very easy for you to figure out. You are wondering what is this E. E isomer versus Z isomer. 𝐸𝐻𝐺 and 𝐸𝐻𝐺. Cis trans basically. Yeah. E stands for 𝐸𝐻𝐺, which basically means opposite in German. And Z stands for 𝐸𝐻𝐺, which stands for same in German. Okay. So your trans type of an isomer is known as E because this and this are on the opposite sides, and your cis type of isomers are known as Z. Okay. Okay. So over here, since bromine is higher priority than this CH3 on this side, and on this side this entire thing is of higher priority. So can you see bromine and this higher priority group are on opposite sides of each other? That's why all of these cases are E. But thankfully you don't have to worry about E versus Z. All of them are E. So forget about it. Yeah. Now you have to figure out what's the answer. क्या होना चाहिए जी? What should be the answer? Lower numbers overall are preferred, right? So if I start the numbering from here, looks good. Okay, so there's a 2 bromo and the double bond is also on 2, and therefore the E also comes on 2. 2 bromo hex 2 ene 4 ine. This is the correct answer. Basically, lower numbers overall are preferred. Yeah. If you are wondering why not this one or why not this one, overall numbers are higher. Yeah. This is overall numbers are lower. This is a 5 4 2. Yeah. This is 2 2 4. Better. Okay. And if you have a difficulty remembering these, there's a very cheesy method that I will tell you to remember these. E stands for opposite, but think you're an Italian and you're like, E stands for opposite. E opposite. Z stands for same. Same, opposite. Okay. Omar is asking why not B about, see, Y will come later, right? E will come first, Y will come later. So ine will come at the end because it starts with a Y, and E will come before ine. Yeah. Surya, if you've noticed, while solving the questions, I am going deep into the concepts as well. And if you want to go deeper into the concept, then you should watch full classes of mine. All you have to do is go to youtube.com and search for Epic GOC. Okay, just search for this Epic GOC. You will see a series of 10 classes of mine on general organic chemistry. And if you study this, then you will guaranteed become an expert at general organic chemistry for sure. Okay. Someone knew, when did I become a Russian, bro? Talking about Italians and Germans, where did Russia come into the picture from? Okay. The IUPAC name of ethylidene chloride is, this is why I hate JEE Main. Okay, JEE Main will ask you about structures that there's a high probability you've never even heard of those. What is ethylidene chloride now? Only if you know, you know. So ethylidene chloride is this. It's essentially a geminal dihalide of ethane. Surya, all of my classes of organic chemistry are available in English. Okay, don't worry. You search for whatever class you want to search for, just write Pahul Sir something English at the end of it. You will find classes from Catalysis by Vedantu channel and very old videos from Vedantu JEE channel. All of those are in English, so don't worry about it. Only my very recent videos on Vedantu JEE channel are in Hindi. Only in the last 6-7 months I've been teaching in Hindi. Before that I always used to teach in English. Alright. So yeah. So whatever. Batao, I mean, tell me what's the answer to this? 1,1-dichloroethane. So again, if such a question comes in your examination and you have no idea what this is, then skip this question. Don't risk negative marking. Alright. The Black Ops, yes, you can study from that channel as well. All of my old videos are good. Sri Chandra, no bro, I don't know Tamil. I don't know Tamil, I don't know Telugu. I just know like 5-6 sentences in Kannada. That's all. Anyway, chalo. Finally, JEE Advanced questions. So towards the end of this class is going to end in the next 10-15 minutes, depends on how long we spend doing these questions. So I have kept a couple of JEE Advanced questions so that we have some fun. Yeah. Let's do this. Newman projections P, Q, R and S are shown below. So we've already seen Newman projections in the case of butane, right? So we understand them decently well, and I will solve this question along with you to make sure that you understand this question thoroughly. Which of the following options represents identical molecules? Are P and Q identical to each other? Are Q and S identical? Are Q and R identical? R and S identical? What's going on over here? It's a very beautiful question. It involves you understanding not just the concepts of Newman projections, but how to convert a Newman projection into a Fisher projection. This is a very good question. So now only those of you who are actually serious about studying organic chemistry, sit here, solve this question aaram se with me. Take your time. Harithan is saying, do advanced questions need to be tough for just the namesake? I mean, pretty much. Why would they call it JEE Advanced otherwise? But yeah, man, they don't want any random human being to get into an IIT. Great for JEE 2024. All depends on the time, bro. When I joined Vedantu back again in March this year, there was a vacancy. You know, we started with catalysis by Vedantu. Pulkit sir and I were working on catalysis again. And then we had this thing at Vedantu JEE where there was a need for chemistry teacher and maths teacher. So we moved there, and since Vedantu JEE was a Hindi channel, I started teaching Hindi as well. Now that we've resurrected the English channel again, I was requested to come here and start teaching here as well. So it just depends on the requirement of the entire organization, buddy. Cool. How do we do this, people? So you need to be able to visualize these structures properly. And to visualize these structures properly, I'm going to give you this example. I'm going to take the structure P, do all the mathematics and science that needs to be done with the structure P, and the remaining structures you can try to figure out on your own. Okay. So let's just focus on the structure P. What I'll do is I will isolate that structure properly. Just give me a moment. So अच्छे से I will isolate. Okay, we will understand how to think about visualizing this structure in terms of different projections. So this is the first Newman projection that you're starting with. My dear friends, do one thing. Make an eclipsed Newman projection. Okay, make a Newman projection that is eclipsed in nature. Okay, what we'll try to do is, let's try to rotate the front carbon to get this CH3 overlapping with this CH3. Okay, let's get these two CH3s overlapping with each other. Let's try to do that. So the first conversion that I'm trying to do, the carbon at the back, I'm not touching it at all. That remains the same. OH, there's a CH3 over here, there is a CH3 here, and the front carbon I'm going to rotate just by 60 degrees clockwise so that this CH3 comes here. Yeah. This CH3 comes towards the OH group, and this C2H5 now overlaps with the CH3. Yeah, this is what we have, sort of. So this is an eclipsed conformation. Now this eclipsed conformation, you're looking at it from this side, okay? You're looking at it head on. What if you look at it from this angle? This is what you're looking at it like. What if you look at it from a slightly different angle? So what I will do is, this is what it is right now. I'll try to look at it from this angle. Yeah, just from the side. Let me draw that for you. So now we're going to convert this Newman projection into a sawhorse projection. Alright. So what we will do is, we'll make a line like this. This is the front carbon, this is the back carbon. Okay. This is the front carbon. Let me highlight it in blue so that we understand which carbon it is. And on this blue carbon, what's going on is, at the bottom you have a C2H5. On the left side we have a CH3, and thankfully on the right side also we have a CH3, so the structure is simple, but for the sake of practicing we are practicing it like this. Yeah. And then on the red carbon, the carbon at the back is, let's say, the red carbon. Why did I choose the green color? Just a second. Yeah. So the red carbon, at the bottom you have a CH3. On the right hand side you have another CH3, and on the left hand side you have an OH group. Now my dear friends, to convert this into a Fisher projection, what do? You look at it from the top. You look at it like this. Yeah, you look at it like this. So if you look at it from the top, what will you see? You will see this CH3 and OH like this. Yeah. You will see this CH3 going away from you. This CH3, this is going away from you. This CH3, this OH, it's coming towards you like this. So you look at it from the top, okay? You convert it into a Fisher projection. This is our central line. This is the carbon at the bottom. This is the carbon at the top, okay? Now it's very simple. On the carbon at the top, on the right hand side, you have a CH3. On the left hand side you have an OH group. On the carbon at the bottom, the blue carbon, on the right hand side you have a CH3. On the left hand side you again have a CH3. And what's remaining now? This C2H5 going towards the bottom, and this CH3 going away from you on the red carbon. My dear friends, there you go. Fisher projection is done. Nice, right? I did this exercise with you just so that you know how to convert a Newman projection into a sawhorse projection, into a Fisher projection. Do we really need to do that in this question? Not really. Because you realize this is not a chiral carbon, neither is this a chiral carbon. On this carbon there are two CH3s, or even on this carbon there are two CH3s. So neither of these carbons are chiral carbons. We don't need to worry about optical activity, we don't need to worry about accuracy of, the structures that we draw over here. I just did this with you to revise the theory, as a lot of you have been asking me to do, to convert a Newman projection into a sawhorse projection, into a Fisher projection. Cool? Omar, yes, it's advised to convert it into such type of an eclipsed conformation, because in a Fisher projection, okay, what happens in a Fisher projection is, let me remind this idea, let me revise this idea for you. If this is your Fisher projection, let's say, the Fisher projection means that whatever bonds are present on the horizontal plane are coming towards you, okay? So this is how you think about them. They're coming towards you, okay? And whatever bonds are on the vertical line are going away from you. So this bond is going away from you, this bond is going away from you. So can you see, this is exactly what you see when you look at this structure from the top view. Yeah. If you look at this structure from the bottom view, then you will see the opposite of the Fisher projection. So if you look at it from the bottom and try to write this, that will be incorrect. In a Fisher projection, it's implicitly understood that the horizontal bonds are coming towards you. So that's why we chose to convert this into an eclipse form, where if I look at it from the top, this OH and CS3, these are coming towards me. Yeah, so that's why this specific procedure. Although, as I said again, in this question, it's not necessary for you to go through this hassle because these are not optically active carbons, so you could just draw them without worrying about the projections. Surya, if you are zero at organic chemistry, you can master around 40% of it in a month properly. Yeah. So you should target getting all of your organic sorted by the second attempt, but by the first attempt you can easily do like 40-50% of it. You can refer to my classes for it if you want. If you guys want me to take a strategy session on organic chemistry, how to master it in the last 30 days, what's the best procedure, etc., you can let me know. I'll take a class on that as well, maybe day after tomorrow. Warm water. Prem Kumar, I'll try to do that, bro, but since this channel is JEE English, I'll focus more on JEE questions, although these questions are good for your NEET preparation as well. Chemistry syllabus is the same. Chalo, theek hai. So coming back to, where is it? Let's come back to this question. This question is not that difficult, as I told you. Simply what we'll do is we'll just draw the bond line formula. Okay, we'll draw the bond line formula. So this is the front carbon, this one. Okay, on this I have a CS3, I have a CS3, I have a C2H5, and on the back carbon I have an OH group, I have a CS3, I have a CS3. This is your P. Let's make Q. Dekhte hain what's happening with Q. So this is the red carbon, let's say. This is the carbon at the front. This guy has a C2H5 on it. It has a hydrogen as well. I'm not drawing hydrogen because bond line formulas mein you don't need to draw hydrogen. Then over here, you have this carbon. Usko blue mein kar deta hu main, ye wala, which is very weirdly given over here. There's an OH group over here, there's a CH3, there's a CH3, and there's a carbon over here at the back which has another CH3. Yeah, ye wala CH3 jo hai, this is what I've drawn over here. Cool. So I'm just converting these into bond line formulae so that things are easier for us to look at. Cool. Let's look at this particular structure. The front carbon, let's make it with red color once again. It has a CH3, it has a CH3, it has an OH group, and the rear carbon has a C2H5 and another C2H5. Okay, interesting. What about this one? The front carbon has a CH3, two hydrogens, let's not draw them in the bond line formula. The rear carbon has an OH group at the bottom. There is a C2H5 and there is another carbon with two CH3s on it. This is the carbon. This is the carbon. Cool. Now compare these four structures and see which two are identical. Tell me. Which of the two structures are identical? Which pairs are identical? Not just which two are identical. Are P and Q identical? There is an OH, then the next carbon has two CH3s, then the next carbon has, okay, P and Q are not identical. Nope. Can you see? I started from the OH group, then you have a carbon which has two CH3s, so till here we are symmetric, very nice. But then the next carbon over here you have CH3, CH3, C2H5. Over here you have C2H5 and C2H5. Let's see Q and S. Q and S. Oxygen, CH3, CH3. Oxygen, no, not the same. Q and R, let's check those out. I think Q and R are the same. Yes, I can already see Q and R are the same. Yes. OH, CH3, CH3, OH, CH3, CH3, next carbon C2H5, C2H5, next carbon C2H5, C2H5. Q and R are definitely the same. Let's check out the last option as well, R and S. These two. अब ये दो सेम नहीं था तो ये भी क्यों सेम होंगे? Obviously this is incorrect. Yeah, so the correct answer over here is C. So the question was simple, by the way, but I took the opportunity to revise Fisher projections for you and Sohaus projections as well. Good. Let's do the next question. This is better. This is where that knowledge will come useful to you. So the question read something like this. I didn't write the statements of the question. The question said that this is D-erythrose. You have 4 structures given to you. How are these 4 structures related to D-erythrose? So what is this? Is it a diastereomer of erythrose? Is it identical to D-erythrose? What is it? So these 4 structures you have to figure out what is their relationship with erythrose. My dear friends, option Q and option S, it's very easy to make the Fisher projections. Option P and option R, it's a little tricky to make their Fisher projections. You need to convert them into the right Sohaus projection so that you can easily visualize the Fisher projection. Think about it, take some time, and then I will do it for you, and then we will end the class. This is the last question of today's class, okay? Take some time, figure it out. You have to match the column over here. So over here, optical isomerism is very important. Over here, you have to convert them into proper Fisher projections. Karo, take your time. Samanyu, okay, let me see if I can do that. Someone you just think like this, if any effect is strengthening the bond length will shorten. If any effect is reducing the bond strength, then it is lengthening the bond, as simple as that. बताइए जी क्या कर रहे हैं यहाँ पे? So to make you understand this question, I will not solve it completely for you, I'll solve it partially, you will do it yourself. Look at Q. How do I convert this into a Fisher projection that looks very much like D-erythrose? You do one thing. In D-erythrose, what you need is CHO on the top. Where is CHO over here? This side. So what I should do is I should try to look at this structure from here. Get it? Look at it from the bottom. If you look at this structure from this angle, from the bottom, what will you see? Think. If you look at the structure from the bottom, I'll draw it for you, what it will look like. Okay. So I'm drawing Q. The Fisher projection for Q is what I'm drawing over here. So what you will see is this is the middle line. Let me draw it in red color, just for color coding. Okay. Now this is the red marked carbon, and the other carbon, let me mark it in blue color, is the blue marked carbon. Now on the red marked carbon, what you will see if you're looking at it from the bottom like this, okay, you will see OH group in this direction, OH group pointing towards you, towards the left side. On the right hand side, you will find the hydrogen. At the blue carbon, on the left hand side, you will find the hydrogen. On the right hand side, you will find the OH group. Similarly, the CHO group will be going away from here, and you will have the CH2OH group this way. So if you look at it from the bottom, yeah, let's say you're lying down like this. And these are your eyes. If that's how you're looking at the structure, this is what you will see. So now, do you realize it's very easy to compare these two structures? CHO at the top, CH2H at the bottom. Yeah. Now it's very easy to compare these structures. These two are diastereomers, right? Because this carbon and this carbon are different in configuration from each other. This carbon and this carbon are same in configuration with each other. So one carbon is different, the other is the same. Diastereomers, these can't be mirror images. In mirror images, both carbons had to be the opposite configuration of what is there in the given structure. So these two are what? These two are just diastereomers. Yeah. So Q is basically mapped with 1. Very nice. This one is also simple now. If you figured out how to visualize that, I'm sure you can see this is very easily the enantiomer. Because both the OH groups, when you make the Fisher projection, both the OH groups will be on the left hand side, both the hydrogens will be on the right hand side, which is completely opposite to this one. So try to make it on your own. This will come out to be the enantiomer. Okay. Now how do you convert P and R into Fisher projections? How do you convert P and R into Fisher projections? You basically make a conformer where these two are present at the bottom. I'll make the Sohor's projection for you, from which you can make the Fisher projection. Okay. So for P, this is a diastereomer, let's just write that over here. I'm just converting this into a Sohor's conformation, Sohor's projection, from which you can derive the Fisher projection, alright. So the left hand carbon I will not touch at all. Just a second, CHO, okay, there is a hydrogen going away from you, there is an OH group coming towards you. So the left hand side carbon I have not touched, the right hand side carbon I will rotate by 180 degrees, okay, so that this OH and hydrogen comes towards the bottom, right. So what will that look like now? This is the OH, see, this is the OH, this is the hydrogen. OH is right now pointing away from you, hydrogen is pointing towards you. Once you flip it, the OH comes towards you. Yeah. So this is what it will look like once you flip that carbon by 180 degrees. And the OH will go on top. Now can you see? Now converting it into the Fisher projection is very easy. I am pretty sure you can see this is the Fisher projection. So P is identical. Saravana, did you join the class late? And by the way, people, for those of you who do not know what are optical isomers, for those of you who do not know what is a Fisher projection, for those of you who do not know what is a Sohor's projection, etc., you need to study the entire general organic chemistry properly from EPIC GOC. Okay. So Saravana, what we are actually doing over here is we are trying to visualize these structures to create the Fisher projection. What does the Fisher projection look like? I told you in the previous exercise. Yeah. The exercise that we did with the previous question, we understood how to make Fisher projections from Sohor's projections. We are just doing the same thing again over here. So Saravana, if you have a doubt in just this part, in this just this question, rewind a little, see how I converted the Sohor's projection into, how I converted a Newman into Sohor's into Fisher, and try to do this again. Okay. If still there is a doubt, then this is what will help you, okay? Fine. So all we need to do is just visualize these things. Saravana, all you need to do to convert this into this, okay, is you have to look at it from the bottom. If you look at it like this, that is exactly what you will see in front of you. Okay. Chalo. So this one is remaining. Can you do it yourself, people? Can you please do it on your own? Try it out on your own, okay? I'm sure you'll be able to figure it out easily. Nice. Okay. Luxury and Omar are saying these are diastereomers. Badhiya. Cool. These are diastereomers. You are right. Correct. Very nice. Chalo, people. So, it was a very fun class with you guys. I hope you enjoyed it with me as well. It was interesting for me to speak in English for such a long time after such a long time. I can feel that my fluency is not the same that it used to be, but I'll get back to it in just a week or two. So anyway, Black Caps is asking, will you be taking physical chemistry as well? Navamita ma'am and I will be sharing the load of chemistry amongst ourselves. So we'll see, man. Organic chemistry is definitely my forte. Physical chemistry, maybe some parts of 11th class physical chemistry or maybe some parts of 12th class physical chemistry. I'll see. Inorganic chemistry is totally Navamita ma'am's job. So, physical chemistry, we'll see how to distribute among each other, between each other. Yeah. Omar is saying, missing your sarcasm. It'll come when it comes. When the opportunity presents itself, sarcasm shall arise. Black Caps, yo man. True Vision Media is saying, sir, I want to revise GOC and Isomers. Please suggest me a video. Okay, everyone. So, for those of you who are very new to my classes, let me just show you some resourceful playlists that you can search for, okay? Just give me 1 second. So, what we'll do is, okay. Yeah. So if you go to youtube.com, you search for Pahul Sir and you search for whatever chapter you want, you will see my classes. But in case you want to do quick revision of theory from me, you have to search for Pahul Sir. Let's rev it. Okay, let's rev it, Pahul Sir. If you search for this, you will get a playlist. Catalysis by Vedantu playlist. You view the full playlist, okay? All the chapters that are there in chemistry, I would say almost all the chapters, 1 or 2 chapters like salt analysis are not there, but almost all the chapters are revised over here. Quick sessions, okay? Some of the sessions are very quick. This is the most popular video by far. So there are quick revision videos of all chapters over here that you can utilize for revision. I will be doing this previous year question solving with you for the remaining time before your JEE first attempt. But in case you want to solve tougher questions with me, then there is another series of mine which is called Pahul Sir, Art of Deduction. So this is the playlist. This is made by a student of mine, but you can go to the official playlist of Vedantu as well. Both playlists are almost the same, by the way. So over here, you will find question solving classes for all those chapters. Really amazing high level questions have been discussed in these particular classes. Okay. Otherwise, whatever you want to learn from me, let's say you want to study biomolecules, just type it out. Yeah. This is Vedantu JEE recently streamed, so these will be in Hindi. Okay. Catalysis by Vedantu, classes will be in English. That's the trick to it. So Vedantu JEE, most classes will be in Hindi. Catalysis by Vedantu, all classes are in English. And if you guys want to study general organic chemistry from me, then you don't even have to write Pahul Sir, just write Epic GOC and you will get it. the first playlist. This is a Vedantu JEE playlist, but it's a very old playlist, so it's all in English. Alright. So you can check this out. Really well made videos, lecture 1 to lecture 10, and you will guaranteed become an expert in organic chemistry after this particular series. Cool? Chalo. So just a quick brief for all of you who are new to my classes. Okay. There you go. So you can check out my earlier playlists on catalysis by Vedantu. Brilliant videos, by the way, all of them. Black caps, I know, man. Those intros were. Haritanam, yeah, I'm always thinking about doing that, rejuvenating catalysis by Vedantu. But the thing is, all of my time goes into this channel, now this channel and Vedantu JEE. So I'm figuring out that if I'm taking classes over here and on Vedantu JEE, what do I do on catalysis by Vedantu? Is there something special or is there something different that I can start over there? So yeah, let's see. Prem, you will find all of those playlists on catalysis by Vedantu. Yeah. If you want to watch my classes for organic chemistry, detailed lectures, you will find all of those playlists very detailed on catalysis by Vedantu. Just go to the playlist section and click on created playlists. Okay, you'll find all of that. Someone new, I am not sure about the all-nighter session when, but I will do it. Just let my throat become a little more lucid. I don't know. Cool. Yeah. Chalo. We'll keep doing beatboxing and stuff later on. Today my throat is all tired right now. Chalo. So the PDF, now one more thing, everyone, new students of mine, my PDFs will only have questions. Okay, whatever text, whatever stuff I've written, this will not be in the PDF. Two reasons. Number one, I don't believe in spoon feeding. If you are spoon fed PDFs by teachers, you will never make notes on your own, and these PDFs will hardly ever be useful, trust me. Second thing, the software that I use on the blackboard over here, this does not save my writing. Why do I not use the software used by other teachers? Because I use the eraser quite a lot, and the other software that all the other teachers use, it doesn't have the quick eraser like this. If you've seen my classes carefully, you see I make lots of mistakes while writing. So I need to erase things to make sure I'm writing correctly. So I need this quick eraser, man. So yeah. You must have a Telegram channel as well, right? So I will just have a word with the team. I will get added to the Telegram channel as well. And once I have the access to post PDFs over there, I'll share this PDF, the questions with you guys. All right. Chalo, theek hai. Thank you so much, people. My throat is hurting now. I'll go chill, perhaps go to sleep after reaching my home. Thank you so much for joining in. I'm going to see you on Friday on this channel. And on Friday, I think at 6 p.m, we are doing that refresher session for reaction mechanisms and alkyl halides. Yes, so we'll discuss quite a bit of theory of alkyl halides and reaction mechanisms in Friday's session. See you then. Bye bye. Take care. Thank you so much for joining in. Good night.